Next, let's consider forecast accuracy. And we had talked about accuracy as being the difference between the predicted value and the actual value. So we're just going to use the naive forecasting method to give an example. And that is where the naive forecasting is where we take the most recent value in our data to predict the future value. And then we're going to show how we get the different components that we use to make these different type of errors: the mean forecast error, the mean absolute error, mean squared error, and so on. So here's what we would get with the forecast prediction based on the time series that we see in the second column, time series value. The 17 from week 1 becomes our forecast for week 2. The actual value in week 2 is 21. So we subtract 17 from 21 and we get a forecast error of 4. The absolute value of that error is 4 also. The squared forecast is 16. The percentage error is going to be 4 divided by 21, or 19.05%, and the absolute of that is 19.05%. Next, we take 21 as our forecast value for week 3, and the actual value for week 3 is 19. So the forecast error is -2. Absolute value of that is 2. The squared is 2. Percentage error is -2 divided by 19, or -10.5. And then the absolute percentage is 10.53. And so we're going to go through those in turn, and we compensate for the negative numbers so they don't offset each other and we get a lower value by taking the absolute value of the errors. Because we're not interested in the direction of the error, we're just interested in that we have errors and we want to figure out how big an error problem we have. So these are the components that we will then use in other errors. So let's take a look. So we have our forecast error is equal to y, our actual y value minus the y hat, or predicted value for that particular time period. And then the mean forecast error is going to be the sum of all those errors divided by n, the number of observations, and then k, which is the actual number of values it takes to make the estimate. And we'll see that obviously in the naive, it's not going to be a large number, but in moving average or exponential smoothing, we may get into some larger values for k. And then the mean absolute square error is where we take, instead of the error value itself, we take the absolute value of it. And again, that way we don't offset the minuses from the pluses to get a lower error rating. Same thing with the mean square error. We're not going to have the pluses and minuses offsetting each other that way. And you can see the formulas for each of those right here. And then we can compare the different methods and decide the accuracy of different forecasting methods. So we could take the naive method, we could take the average of past values, where we then sum all the past values and then get an average. And we can compare the different error types we get, the mean absolute error, the mean squared error, the mean absolute percentage error, and we can see what which of the two approaches gives us a better, a lower error rate for our particular data set. So error is something we want to consider. We want to obviously come up with something that gives us the lowest possible error rate. Okay, next let's consider moving averages and exponential smoothing. And with a moving average, we take the most recent K values in our data set, and we based our forecast on those most recent K values. So we take the average of the most recent K values. So we sum up their values. Let's say the most recent 3, we sum up the most recent 3 values and divide by 3. In other words, we take the average of those. And then that's going to become our estimate for the future. And it's going to be where we take I from t minus k plus 1 to t. So then we have k values that we're going to be going with. And then we divide that sum by k. And again, y hat is our forecast for the next time period. Yt is the actual value for a particular time period, and k is the number of time periods that we use to generate the forecast. So let's take a look at this. And we'll go back and open up gasoline sales. And it's opening now. Okay, I'll share this. So when we have the most recent K values divided by K, a smaller K will track changes better. In other words, if we make it like 2 or 3, that's going to show most recent impacts on our data set. A larger K, like 6 or 7, is going to smooth out the fluctuations better. So let's take a look. Now, in this particular case, we're going to use our data analysis tool pack. So let's go there. So we go to data, data analysis. And here it is. And we'll go to moving average. Just so happens it opens up on moving average with my version of Excel. So I'm going to select for the input range B1 through that. Labels are in it. And I'm going to put 3 in as an interval. In other words, I want to go back every 3 values. Okay, so then my output range, I'm going to put in C3. Click OK. And then we get our particular values for this. Okay, and let's just select column B here and put in a line chart. And I'm going to now add in this data. here I'm going to add a series in, and this is going to be called move. Oops. Okay, so let's do this again. So now we've got the actual values in blue. In other words, these are our actual results. And then our moving average graph is in red. So this is the estimates based on our moving average of the actual data. So this is how we can come up with estimates for the future with our particular data set, 19, of course, being the value that we would expect going into the future. Okay, now let's switch back. Okay, so we get this particular graph that we just saw, that we did in Excel. And we can apply our accuracy formulas, and we find out that the, again, as we showed before a couple minutes ago, that the 3-week moving average has a better accuracy rate than the naive approach towards estimation or forecasting. Another approach is going to be exponential smoothing, and this is something that uses a weighted average of past time series values as a forecast, and it applies a smoothing constant, and that's a weight given to the actual value in time period t. So the weight given to the value in time period t is actually 1 minus alpha. So alpha is the smoothing constant, and then 1 minus alpha is the damping factor. And so here's an example of exponential smoothing. So the forecast value for y hat sub 2, the next time period, is going to be equal to our smoothing constant times A1 plus the damping factor times our estimate for Y1. So we take the actual value for Y1 and the estimated value for Y1. We apply the smoothing constant to the actual value and the damping factor to the estimated value. And then we come up with our forecast for the next period. So let's take a look at how we do this. So we'll just come back to our Excel worksheet for gasoline sales. I'm going to just name this move. And we'll call this Expo. So again, we're going to use our data analysis tool pack. And so we go to data, data analysis. Here I'm going to use exponential smoothing. So I open that. My input range will be my values. I do have labels. Now here it's asking for the damping factor. So in this particular problem, the smoothing constant was 2, so the damping factor is going to be 8. And the range we'll put into E2. Okay, so the values I have, my input range is going to be my sales, my damping factor of 0.8. The labels are included in that. The output range is going to be D2. So let's click, see what we get. And so here we get our exponential smoothing estimations of what's going to happen. So now let's go ahead and put this into our graph. So let me right click here, select data. I'll add in another sheet. I'll call this one Expo. And series values are going to be these. Click OK. And now this green line is my exponential smoothing estimate for things. And we can also, click either the moving average or the exponential smoothing and get a trend line in there. We can include the equation if we want, and so on. So right here. So again, this is going to give us exponential smoothing. I also left the moving average in, that's the red one. So, okay, so these are again two other methods for forecasting based on the time values that we see. So let's go back to our lectures. So that was exponential smoothing. And again, this is with a smoothing constant of 2, and we used a damping factor of 8. In other words, 1 minus 0.2 is going to give us 0.8 that we would use. And of course, we can calculate the forecasting accuracy for these. And we would, again, choose an alpha. We could vary alpha and then see what alpha gives us the minimum mean square error, or for something that calculates the error rates that we might have. Okay, so I'm going to close that worksheet, and I won't save those values. Okay, let's go on. To look at a regression in time series forecasting. Now in chapter 7, we looked at regression between two independent variables. Here we're looking at regression with a dependent variable and in time. So last week I meant we looked at, initially we looked at one independent variable and the dependent variable. Then we looked at 2 or more, but in our particular demos, we just used 2 independents against 1 dependent. Here we're going to look at the dependent variable, and we're going to use time as our independent variable, the thing that we think is going to be an indicator of what the value is for a particular sales amount. So again, we can use regression analysis to forecast a time series if it has a linear trend. So a simple linear regression analysis is going to give us the relationship between the independent variable and the dependent. And we want to look at the trend over time as the independent variable. So here's the equation. Obviously, instead of x, in our equation. This one looks very familiar, B0 plus B1 times T. Last week was B0 plus B1 times X. So it's just showing that we're using the time periods as our independent variable. And so then we can pick up a trend line, and then based on that trend line, we can come up with an estimate for next period sales. So, for time period 11, we substitute that in and we get, our value of 32.5. And of course, in the thousands, that's going to give us 32,500. Okay, so let's take a look at this. I'm going to open bicycle sales again. We've had enough with the gasoline sales. And it's opening now. There, well, there, okay. So let me share this. And this is the bicycle.xls file. So we can open that. So again, here we have our data. Just for fun, let's do a visualization. And I'll use a scatter chart this time. So I'll go to Insert, Scatter Chart. And it does appear that over time we have something of a linear looking relationship. And, I can put our trend line in. Okay, so, but let's use our data analysis tool pack. So I'll come over to data analysis. Go down to regression. The Y range is going to be sales. That's our dependent variable. The X range, the independent variable, in this case is going to be year. We did include the labels. We'll make this a 99%. And we see that we get a y-intercept of 20.4 and the slope of the line as 1.1. So from that, we can, of course, determine our equation. And so we can actually come back to our graph and put the equation on there. It's, of course, another way of doing the regression. And we get the same equation. And we could estimate the for the sales for year 11 by just substituting 11 in for X, and you get, whatever the value would happen to be for that. Probably going to be like 32, but it was the one that was calculated in the text. So we just substitute 11 in for X, and we get 1.1 times 11. And so that might be 12 plus 20.4 is going to be roughly 32, and so on. Another thing to consider is that, remember last week we worked with quadratics. So if there seems to be a nonlinear type relationship with time, then we could add in columns of time squared or time cubed and so on and continue on. We can also, if there's a covariance or an interaction between the independent variables, we can add in an X times Y. So there's several things we can do if we wanted to. And the slope of the line in this trend equation indicates that over the past 10 years, the firm has experienced an average sales growth of about 1,100 units per year. Okay, so let's head back to our lecture slides. So we can look at regression as perhaps a causal forecasting tool. The relationship of the variable to be forecast with other variables is going to be used to develop a forecasting model. And this model provides evidence only of an association between an independent variable and the variable to be forecast. The model does not provide evidence of a causal relationship between an independent variable and the dependent variable. And the conclusion that a causal relationship exists must be based on either practical experience. So management thinks that X causes Y, and this association we find confirms their belief. So that might be one approach for using it as a causal forecasting method. Another approach we could take is we could do a control study. So we have a control group, an experimental group. We apply the treatment to the experimental group. In other words, we vary the independent variable with the dependent group. We don't with the other. We see what the differences are. So that's another approach we could take if we wanted to make a causal model. But probably in business, most often what will happen is you'll do a regression analysis for forecasting. You'll get this association. The association by itself, the regression analysis equation by itself, does not indicate causality. If there is going to be a causal model, that has to be based on the practical experience of management. They may say, well, you know, this confirms what we've always been thinking, that X causes Y. So, okay, that might be what you would go forward with at that time. And then finally, let's consider the best forecasting model to use. You can look to do a data visualization to see for yourself if there appears to be a pattern, seasonality, linear, nonlinear, whatever it happens to be. And then look at scatter charts, relationships to see if there's linear or nonlinear relationships. And if certain relationships appear totally random, you might want to exclude those variables from the overall forecast. When you're working with large data sets, again, we talked about big data last week, you want to divide your data into training and validation data sets. And with big data, you may want to do that over a large number of subsets. You know, you might divide your big data into 50 subsets and then divide them into training and validation sets. And then you're going to look at your mean absolute error, mean square error, or the mean absolute percentage error as something to tell you the validity and accuracy of this particular model. And then based on those, you can compare one model to another and decide which one's going to give you the best approach. Naive forecasting, or a moving average, or an exponential smoothing, or a regression. You know, so those are, or a whole winter. These are the ones we've considered for a time series in this lecture. But again, it's, you might have others, but this is an approach you could use to determine the best one, is look at the error rates you get, especially from your, if you divide it into training and validation sets. Okay, and again, just as we said with regression, time series analysis doesn't necessarily show causality. What it shows is an association, but that association may confirm management's beliefs, and they may then say, well, this confirms our belief that X causes Y. But of course, you could always do a controlled experiment where you have a control group, experimental group, and do it the scientific way to really confirm causality. For the most part, what we say is these relationships show an association. If there's going to be causality, that would be you guys have proved it to yourselves, and this is confirmation of that proof. Or you can do it officially with control groups and so on. Okay, any questions?